In the last lecture, we were using separation of variables procedure to solve the problem of two slabs that are brought into contact, two different temperatures, but made of the same material and made of the same thickness, brought into contact at time t is equal to 0 in such a way that the outer surfaces of both slabs are insulated, so that there is no flux going out from the outer surfaces. And we wanted to examine how the temperature varies as a function of time. Okay. So, this was the configuration that we had. Okay. T is equal to T1 on the top slab, T is equal to T2 on the bottom slab, both brought together at time t is equal to 0 with insulating surfaces at z is equal to plus h and z is equal to minus h. And I had given you a physical picture of how the temperature should evolve. Okay. In the long time limit, the temperature has to be the same throughout the material in the at steady state, and that has to be the average temperature of the two slabs. Okay. So, we had defined scale temperature by subtracting out that average temperature, that steady temperature. Okay. Because it is a constant, I can always use that to define the scale temperature, and therefore, we had the conditions that the temperature gradients are 0 okay, at z star is equal to plus 1 and z star is equal to minus 1. Okay. The temperature gradients are 0 at z is equal to minus 1 and z is equal to plus 1. And the initial condition was a discontinuous condition, that is at t star is equal to plus 1 for z greater than 0 and is equal to minus 1 for z less than 0. Okay. That was the initial condition. The solution procedure was the same as what we had earlier. Express the temperature as a function of t times a function of z, substitute it in the equation, divide by f times z. Then the left side is only a function of time, the right side is only a function of z, and therefore, both of them have to be equal to constants. That constant has to be negative, so that the transient part of the temperature, which in this case is equal to T star, because the steady part is 0. Okay. So, in this case the transient part of the temperature is equal to T star. That transient part has to decrease to 0 in the limit as time goes to infinity, and that happens only if this constant on the right side is negative, and therefore, we had chosen it as minus beta square. And we had got the function z as some constant times beta z star, I am sorry, some constant times sine of beta z star plus some constant times cos of beta z star. And since it had to satisfy the boundary condition that the slope is equal to 0 at plus or minus 1, okay, that constant necessarily had to have this particular form, where I is an integer, 2i plus 1 into pi by 2, where I is an integer. Okay. If it has this particular form, then the derivative, which is the cos function, will be 0 on both surfaces. Okay. The slope of the sine function will be 0 both at z is equal to plus 1 and z is equal to minus 1. So, therefore, we had this solution for t. Okay. We had this solution for t. Some coefficient a I times sine of 2i plus 1 pi z by 2 times e power minus 2i plus 1 pi by 2 the whole square into t. Okay. So, that was the final solution. This solution satisfies the equation, because it satisfies the equation for any value of beta, okay, the left and right sides are equal, and it satisfies the boundary conditions that the flux is equal to 0 on the top and bottom surfaces. It satisfies the boundary condition that the flux is equal to 0 on the top and bottom surfaces. It does not yet satisfy the initial condition. At t is equal to 0, this temperature was some discontinuous function. T is equal to plus 1 for 0 less than z less than 1, and is equal to minus 1 for minus 1 less than z less than 0. Okay. So, it does not yet satisfy the initial condition, that is that this summation has to be equal to plus 1 on the top half, it has to be minus 1 on the bottom half. How do we satisfy this condition? Using the orthogonality relation. Okay. Multiply both sides by sine of 2j plus 1 by z by 2 and integrate. From over the entire domain, okay, integrate over the entire domain. So, that is the procedure, the standard procedure that one would use in this particular case. Okay. So, if I apply that procedure, okay, I can take the summation and I outside, I am sorry, summation ai, integral between minus 1 and 1 dz star sine of 2I plus 1 by z star 2 sine of 2j plus 1 by z star by 2. Okay. Is equal to 1 for 0 to 1, okay, it is equal to 1 for 0 to 1. So, that from 0 to 1, okay, I have to multiply 1 by sine of 2j plus 1 by z by 2, okay, that is from 0 to 1, I have to multiply it by 1, and from minus 1 to 0 I have to multiply it by minus 1, okay, so I get a minus sign here. Okay, from minus 1 to 0 there is a negative sign, it is equal to minus 1. So, I have to integrate minus of sine 2j plus 1 pi z star by 2. Okay. So, by equating the left and right sides I should be able to get a solution for the functions a. Okay. So, let us calculate these two integrals one by one. Okay. Integrals minus 1 to 1. Simplify this using the same identity, sine A sine B is equal to half of cos of A minus B minus cos of A plus B. Okay, that is the same identity. Okay. So, this is equal to half integral 0 to minus 1 to 1 dz, okay, sine of, I am sorry, this is cos. Okay. Okay, this is cos of I minus j by z. Cos of A minus B. Okay. So, cos of A minus B, I will take 2 I plus 1 pi z by 2 minus 2j plus 1 pi z by 2. So, I just get cos of I minus j z minus cos of I plus j plus 1 pi z. Okay, just substituting this identity in here. Okay, just substituting this identity. Okay, so Now I can integrate the terms. Okay. Integral of cos is sine. Okay. Integral of cos is sine. So I get half into sine of I minus j by z star, okay, by I minus j pi, okay, minus sine of I plus j plus 1 by z star by I plus j plus 1 into pi, okay, between minus 1 and plus 1. The two limits of integration between minus 1 and plus 1. Okay. I and j are integers. Okay. I and j are integers. Sine of I plus j plus 1 pi z is always 0, okay, because any integer times pi, sine of that has to be 0 for both z is equal to plus 1 and minus 1. Okay. So, the sine function here has to be equal to 0. The first term as well, that sine function has to be 0, okay, for all integer values of I and j. Okay. Therefore, this is also 0 provided I is not equal to j, so that the denominator is finite. Okay. If I is not equal to j, the numerator is 0, the denominator is finite, and therefore, you basically get 0. Okay. So, therefore, this has to be equal to equal to 0 for I is not equal to j. Okay. For I is equal to j, both the numerator and the denominator, okay, for I is equal to j, both the numerator and the denominator tend to 0. So, what you will get is that this will be equal to half of sine of I minus j pi by I minus j pi, that is the value at z star is equal to plus 1, that is the upper limit, okay, minus the lower limit, which is sine of minus of I minus j pi by I minus j to pi. Okay. So, the first term at the upper limit when z is equal to plus 1 gives you this, and the first term in the lower limit when z is equal to minus 1 gives you the second term. Okay. And you can see that sine of a minus something is equal to minus sine of that. Okay. So, this basically becomes equal to sine of I minus j into pi by I minus j into pi, okay, because both terms in this are equal. Okay, you are adding up two equal terms, and therefore, you get just that half factor cancels out, and this just becomes equal to 1 for I is equal to j. Okay. Just doing the integration, you get this is equal to 1 for I is equal to j. So, which means that this is equal to 0 for I is not equal to j, it is equal to 1 for I is equal to j. Okay. So, it is equal to 0 for I is not equal to j, and this is equal to 1 for I is equal to j. Okay. Therefore, this product is just equal to delta ij. The Kronecker delta that we had seen earlier, it is equal to 1 when I is equal to j, and it is equal to 0 when I is not equal to j. So, once again, this product is non-zero only when I is equal to j, okay, otherwise it is equal to 0. Okay. This product is non-zero only when I is equal to j, it is otherwise 0. Therefore, I get on the left side I will get sigma I is equal to 0 to infinity a I times delta I j on the left side, okay, a I times delta I j on the left side. On the right side, I have to evaluate these two integrals. Okay. On the right side, I have to evaluate these two integrals. Okay. Let me call this as 1 and let me call this as 2. So, I will now evaluate the two integrals on the right side. Okay, so 1 is equal to integral 0 to 1 dz sine two j plus 1 by z by 2. The integral of the sine function is a cos function. Okay, the integral of a sine function is the cos function. So, this will be equal to minus cos, because the derivative of cos is minus sine. Okay, so, this is minus cos of 2j plus 1 by z star by 2 divided by 2j plus 1 by 2. Okay. This is evaluated between 0 and 1. Okay. At z is equal to 1 for any integer j, okay, at z is equal to 1 for any integer j, the cos function has to be equal to 0. Okay. At z is equal to 1 for j is equal to 0, you get cos of pi by 2, for j is equal to 1 you get cos of 3 pi by 2 and so on. Therefore, at z is equal to 1 it has to be 0, okay. And at the lower limit at z is equal to 0, this cos function is 1. Okay. The lower limit at z is equal to 0, this cos function is equal to 1. Okay. Since the integral is the upper limit minus the lower limit, this just becomes equal to plus 1 by 2j plus 1 pi by 2. Okay. It's equal to 2 by pi into 2j plus 1. Okay. That was the first integral that we had, on the right side. Okay. The second one is equal to integral 0 to minus 1 to 0. Okay. Which is the same thing, except it is now between minus 1 and 0. Except that is now between minus 1 and 0. Okay. At minus 1 the cos function is 0, okay, for any integer j. Okay. Cos function is the same for positive argument as well as for negative argument, it is the same. Therefore, at minus 1 it is 0, at 0 it is 1. So, this is equal to minus 2 by 2j plus 1 into pi. And the right side is equal to 1 minus 2. Okay. So, I get on the right side is equal to 1 minus 2, which is equal to 4 by pi into 2j plus 1. Okay. Because 1 is positive, 2 is negative. Okay. 1 is positive, 2 is negative. When I take 1 minus 2, I just get 2 times that, 4 by 2j plus 1. Okay. And on the left side I have ai times delta ij, and ai times delta ij has to be equal to 0 when I is not equal to j. Okay. So, all the coefficients are all 0 when I is not equal to j, and it is non-zero only when I is equal to j. Okay. Therefore, this becomes equal to aj. And my solution T star is equal to summation, okay, I is equal to 1 to infinity a I, which is 4 by pi into 2I plus 1, okay, sine of 2I plus 1 pi z by 2, okay, times e power minus 2I plus 1 whole square whole square into t star. Okay. So, this is the final solution that we have. Okay. This is the final solution that we have, and you can plot this solution once again, and the conclusions are very similar to what we had earlier. You can approximate the solution by retaining just a finite number of terms in the series. If you retain just one term in the series, the solution is numerically accurate for t star greater than about 0.1. Okay. If you retain 3 terms in the series, you can go down to 0.03. However, at 0.01, 3 terms is not sufficient. Okay. You need to retain a larger number of terms. So, depending upon the time from which you want an accurate solution, you can use an adequate number of terms in the series, so that you get a numerically accurate solution at that particular time. At time t is equal to 0, the function is actually discontinuous. Okay. So, I'll try to briefly give you first a physical understanding of what we are doing when we do this separation of variables. And intriguingly, you would have found that in both the problems that we had solved, when we took a function beta I sin I pi z multiplied by sin j pi z and integrated it, it was 0 if I was not equal to j. That was in the first problem of conduction into a slab. The second problem as well, when I took one function for a particular integer value and multiplied by the same function for a different integer value, it was 0 unless the two integers were the same. And that was basically what had helped us to solve this orthogonality relation, because the original orthogonality relation that I have, right, it contains an infinite number of terms on the left side. But when I multiplied it and integrated it, all terms became 0 except for 1. And that was what had enabled us to solve this problem. Okay. So, in the next lecture, I will briefly look at why we get these orthogonality relations, okay, the reason for orthogonality relations. But before that, let me just briefly tell you what, give you some physical understanding of what we are solving here. The original problem, okay, t star is equal to 1, t star is equal to 0, z star is equal to 1, z star is equal to 0. Okay. This is the steady temperature. Okay. This is the initial temperature. It is equal to 0 everywhere. It is equal to 1 at the surface. Okay. So, it is basically a step function. Okay. Okay. So, this is the initial temperature. Okay. This is at T star equal to 0, this is the temperature. Okay. And this is for T star going to infinity. Okay. I had expressed the temperature as Ts plus Tt. Okay. Therefore, at T is equal to 0, okay, the transient temperature was equal to minus the steady temperature. Okay. That means that the transient temperature looks something like this. Okay. So, it is negative of the steady temperature. Transient temperature is 0 at the bottom surface because there is a discontinuous change in the temperature there. Okay. The transient temperature is 0 at the bottom surface because there is a discontinuous change in the temperature there. It is equal to the negative of the steady temperature. Okay. At initial time, effectively from my solution, I had got the transient temperature as equal to summation of An sine of Ai times I pi z. That was the solution that I had got for initial time. Okay. So, if I plot these functions, okay, if I plot these functions, okay, for different values of I, okay, for I is equal to 1, right, it goes from 0 at the bottom surface to 0 at the top surface. Okay. So, it looks something like this. for I is equal to 2, it starts from 0 at the bottom surface, increases to 1 at pi by 2, decreases, okay, and then it goes, it is 0 in between, okay, then it goes like this. So, this is the solution for I is equal to 1, I is equal to 2, and I is equal to 3 will have 3 lobes. Okay. This will be for I is equal to 3, okay, and so on. Okay. So, this is equal to minus of 1 minus z. Okay. This is equal to minus of 1 minus z. So, basically this initial condition, this blue initial condition here, okay, this initial shape of the profile, okay, I am expressing it as the sum of these sine functions. I am expressing the initial shape of the profile as the sum of these sine functions, okay, and I am evaluating the coefficients of the sine functions using the orthogonality relation. Okay. So, basically what I am saying here is that this initial profile, okay, is equal to some coefficient times this one plus some coefficient times this plus some coefficient times this plus etcetera. Okay. And this discontinuous function I am expressing it as the sum of continuous functions, and I am getting the coefficients in this series uniquely, okay, using the orthogonality relation. Okay. So, basically we are expanding this in a set of series of basis functions. We are expanding this in a series of basis functions. These basis functions for this particular configuration are sine of I pi z, and we are getting the coefficients such that the infinite sum of these basis functions is equal to this initial condition, okay, which could be discontinuous. Okay. Okay. So, that is physically what we are doing when we do this similarity solution. Similarly, for the second problem that we had, okay, okay, the final temperature was just a constant value. Okay. The initial temperature was something like this. Okay. When I expressed T star at T equals 0, okay, that was the initial condition. Okay, it was plus 1 for the top half, minus 1 for the negative half, bottom half. Okay. And we had expressed this as a function of as T star is equal to summation of AI sine 2i plus 1 pi z by 2. Okay. This has to be equal to 1 for z greater than 0 and it is equal to minus 1 for z less than 0. Okay. Okay. So, that was the initial condition. Okay. So, if you look at the terms here in this series, right, they would look something like the first term, okay, would look something like this. Okay. The second term would look something like this. Okay. Okay, the third term would have more lobes here. Okay. So, basically what I am doing is I am representing this function, I am representing this function as a1 times something that has 0 slope at the surface. Okay, so plus a2 times something that has 0 slope at the top, okay, plus a3 times something that has okay, plus etcetera. Okay. So, I am just expanding these as a series of basis functions. In this case, the basis functions have to have 0 slope at the top and the bottom surfaces. Okay. That is what is prescribed by the boundary conditions. Therefore, I choose a series of basis functions that satisfy the boundary conditions, and I express this initial condition as a linear sum of all of these. Initial condition is discontinuous. but I can still express it as the sum of as a series expansion in these basis functions which are complete and orthogonal. Why are they orthogonal? We will examine that in a little further detail in the next lecture. I will see you then.